Good morning, everyone. I'm Zhichen Zhang from Tianjin University. Welcome to our series of virtual academic seminars to celebrate the launch of SmartMed. SmartMed is co-launched by Weili and Tianjin University. I'm one of the associate editors of SmartMed. The editors-in-chief of SmartMed are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Now, SmartMed has been indexed by ESCI with the first impact factor of 20.4. SmartMed has also been selected as Zone 1 in Chinese Academy of Sciences Division. Welcome to submit your work to SmartMed. Today, Dr. Cao Shangding from Queen's University will give the presentation. Now, I'd like to briefly introduce Dr. Cao Shangding first. Dr. Cao Shangding is an assistant professor of chemical engineering at Queen's University. He received his PhD degree in chemical engineering from Nava University in 2014. From 2014 to 2019, Dr. Cao Shangding was a postdoctoral fellow in the Department of Electrical and Computer Engineering at the University of Toronto. Dr. Ding's research focuses on developing electrochemical processes for renewable fuel and chemical production from carbon dioxide, water, and renewable electricity. He has published over 100 papers in prestigious journals, including multiple publications in Science and Nature. His work has been cited over 25,000 times. H index is 65 based on Google Scholar data. Dr. Ding is a recipient of the Waterloo Institute for Nanotechnology Rising Star Award and the prize for excellence in research for outstanding emerging researcher at Queen's University. In 2023, Dr. Ding was awarded the Science Breakthrough of the Year 2023 by the Foreign Wars Foundation for his innovative work in carbon capture and conversion. He was listed as a highly cited research in the field of chemistry from 2021 to 2023 by Graduate. Dr. Ding is a founding editor-in-chief of the new interdisciplinary journal, Cambridge Presents Carbon Technologies, published by Cambridge University Press. Today, Dr. Cao Shangding will give a talk about toward practical electrochemical carbon dioxide conversion to hydrocarbons. Let's welcome Dr. Cao Shangding, please. Thank you.
Thank you for your introduction. Let me share the screen.
Yeah, thank you. Please.
Do you see my screen okay?
Okay, now please.
Okay, great. Thank you so much for inviting me. It's such a great honor to be an invited speaker for this wonderful lecture series. So today I'm going to talk about electrochemical carbon dioxide conversion toward practical application. And by practical, I mean high performance, long stability, and the system built on the inexpensive and abundant material. So we are all aware of that, like the carbon dioxide emission has been increasing, continue to increase in the last 30 years or so. And now we are emitting about 50 billion tons of CO2 equivalent per year, right? So among them, about 40 billion tons is CO2. And the CO2, this CO2 emission had caused the global warming. And if we continue to emit the CO2 like what we are doing now, the global temperature can increase up to 4 to 5 Celsius degrees by the end of this century. So And if that scenario happened, then it would be a disaster in terms of the climate change. So if we want to keep the temperature decrease, like below, let's say, 2 Celsius degree, then it's obvious that we need to cut down the CO2 emission. So the problem is not why do we need to do that, but how we are going to do that. So if we look at like where the CO2 come from, then you will see like that like more than 75% of CO2 is coming from the energy, right? So we use a lot of energy, the fossil feedstock to get the energy, and then we emit the CO2. So one of the solutions for us is to transit to the more like low carbon energy, low carbon electricity, like wind and solar and nuclear. But the problem is we do not just use the electricity, right? We use different type of fuels, let's say for long distance transportation, for heavy industry like steel and cement. And also we use the fuels to generate electricity on demand, right? So those are the sector which is quite challenging to decarbonize. Now, the other sector, like short distance transportation or like heating, low temperature heating, like the buildings, it can be straightforward just to electrify them. But that about 20% of the long distance transportation and heavy industry, which is quite challenging to decarbonize. Now, another thing is if we are going to build our energy system based on the wind and solar, then obviously we need to find a way to store them, right? It's not just for day, for hour, but like for years, for months, right? So that is the two big challenge. So one of the solution is that instead of trying to electrify like, on the industry, on the transportation, we can electrify the fuels, right? So we can make the fuel with a low carbon footprint so that we can keep using the fuels, but we do not emit new CO2. So the way we do that is that if we can make fuels and chemical starting from the CO2, let's say CO2 captured from the atmosphere, and then you make fuels like from that CO2. So when you burn the fuels, you emit the same CO2. So it's called the carbon neutral fuels. Now, of course, in order to get the carbon neutral, the energy to convert CO2 to fuels need to come from the low carbon energy, right? Like wind and solar. So by doing so, you can also store the wind and solar in the form of the chemical fuels, right? So not just making carbon neutral, but also you find a way to store the renewable electricity. So the technology that I'm working on is one of the solutions. So it's called electrochemical carbon dioxide conversion. So in principle, it is a electrochemical process. So you use the electricity to drive a chemical reaction. Now, in this technology, you can use wind and solar, the electricity from wind and solar, and then you drive the electrochemical conversion of carbon dioxide like into different type of products, right? So you use the electricity, break down the CO2 molecule, break down water molecule, and then combine those atoms together into like fuels, into like chemical polymer precursor. But if you know how to break the CO2 molecule and nitrogen molecule, then you can also like make the fertilizer like directly with this process. Right? So now fuels and chemical just coming from CO2 and renewable energy. So that fuel and chemical have a low carbon footprint. Now this sounds amazing, like we can make fuels and chemicals with this process, but in fact, it's not so straightforward. So I just want to give you an idea of how we perform electrochemical CO2 conversion and what is going on when a CO2 molecule get into a reactor. Right? So in the first step, you will have the CO2 molecule like diffuse through a porous layer, like some porous layer to get to the catalyst where it is converted. So this one is just the CO2 from the gas phase. And then it goes to the interface here, like the interface between the gas phase and the liquid phase, right? So now if you zoom in this small area, now the CO2 gets to the interface between gas and liquid. Now it needs to diffuse inside the liquid phase, right? And to reach the surface of the solid, here the surface of the catalyst. And here is interesting thing happen. Now the CO2 molecule is going to adsorb on the surface, and then it's going to be converted to some intermediate, and those intermediate combine with each other and form the final product. Now in this case, like we're making the ethylene, for example, right? So you have the two CO2 molecule combined, and then you form the ethylene. Now along the way here, like CO2 coming from the gas phase until it goes through the liquid phase and then it produces product. Those are like multiple steps. And every single step here will affect the efficiency of the process. And that's why it's quite challenging even to bring the CO2 to the surface of the catalyst. That is already a challenge that I'm going to show you why. But in general, if you want to make a very efficient CO2 conversion, you will need to find a way to control every single step, right? So that you can make the product that you want, you can improve the efficiency. Okay, so the main focus of my talk today, I'm going to talk on 3 different topics all related to electrochemical CO2 conversion. So the first part, I'm going to focus on how to bring the CO2 molecule directly from the gas phase to where it should be, which is on the surface of the catalyst, right? Okay, so here the challenging part with electrochemical CO2 conversion. Now, in order to convert the CO2, let's say to hydrocarbon, right? So we need CO2 molecule, often in the gas phase. And then you will need the proton, right? If you want to make hydrocarbon, ethylene, methane, ethanol, you need hydrogen, right? So that hydrogen mainly coming from the water. So you need CO2, you need water. And then you will need electron, which is coming from the anode to the cathode. And then the electron needs to be in an electrical conductive substrate, right? So in principle, you will need a solid that is conductive, and then you need CO2, and then you need water. So that one, often a 3-phase interface, bring them together. And that is quite challenging to bring 3 different components at 3 different phases. But it's not kind of like something unusual because like over 50 to 100 years ago, like fuel cell technology has already identified the way to overcome that. And the way that we overcome this problem is using the gas diffusion layer. So on the right-hand side here, I'm showing a porous gas diffusion layer, often a hydrophobic one, and it's conductive. And then you deposit the catalyst on top of that, right? So the gas diffusion layer, often they are made of carbon particle, and then you combine with the polymer, hydrophobic polymer like PTFE. So you mix carbon, which is conductive, PTFE, which is hydrophobic, and then combine them together to make a porous, conductive, and hydrophobic. So the hydrophobicity of this layer will prevent the water to penetrate there. It allows only CO2 to go through, right? So CO2 goes through this porous layer, water coming from the liquids, all of them meet on the surface of the catalyst layer. So that's work perfect, right? So we bring 3 components together. So about I think 6 or 7 years ago, when we started working on this technology, we use exactly the same gas diffusion layer that people use for the fuel cell technology, right? So carbon-based gas diffusion layer, and then we spark a thin layer of the catalyst on top. So we use the physical deposition to grow a thin layer of the metal. In this case, we use the copper on the surface of the carbon gas diffusion layer. It looks something like this on the left here. And it worked perfectly when we ran the CO2 conversion in a alkaline electrolyte we get pretty high selectivity for ethylene in this case. So CO2 conversion to ethylene with a Faraday efficiency of 50 to 65%, which is pretty high for the current density from like 200, but it's pretty high at that time. Now the people report like 80, 70, 80%, but by that time it's pretty high. Now the problem with this is that when we run the stability test, right, so we keep the reaction as a fixed current, and then we monitor the reactor over time, the product over time. And as you can see here, now the ethylene selectivity dropped pretty quickly after like half an hour or so. And at the same time, the hydrogen keep increasing. Methane and CO stay pretty the same, right? So this suggests that if something happened. And when we look at the back and the front of the gas diffusion layer, and we found that it turned from the hydrophobic into the hydrophilic, right? So there's a different mechanism that why the carbon changed from hydrophobic to hydrophilic. But the bottom line is that now that the porous layer become hydrophilic, and then the water penetrates inside the pore of the gas diffusion layer, and then it blocks the diffusion of CO2. Now that you do not have the CO2 to reach the surface of the catalyst, and that's why we do not have CO2 for the conversion, and we produce the hydrogen. So by that time, we came up with the idea of why should we use the carbon gas diffusion layer, and can we use something which is more stable? So I look at like different type of porous substrate that can be used for gas diffusion layer. And I found like this, on the right-hand side here, you can see a bunch of filter. It's basically the filter for non-polar solvent. So it must be hydrophobic, right? This is basically, I cut all of the plastic outside, and then you have the small filter inside, and then we deposit the catalyst on top of that. So it's like on the left-hand side here, you see a porous PTFE layer, and then we deposit the copper catalyst on top, still the same with the physical deposition method. And then we add another carbon layer to increase the conductivity. Now, you see like now with the new configuration here, now we do not combine PTFE and carbon in a single layer, but we make them two separate layers with the two different functions. Right? This PTFE only allows the CO2 diffusion. We do not need the conductivity here, but we add the carbon on top to increase the conductivity. Now we decouple the function of the two layers. And it's working just perfectly. Now like you have the PTFE layer, which is pretty stable. And then we run the reaction at, I think at the current around 100 milliamp or so. And then we can see that the ethylene here, when we use with the PTFE substrate, it can maintain at around 60-70% for like over 100 hours. Now, by that time, I think it's one of the longest one for CO2 conversion to ethylene. Now, in comparison to the carbon, as you can see here, the black symbol here, now it dropped like within an hour. And also, we look at the substrate after the reaction, and just to see why it's not so clear, but we can still see the copper layer like sandwiched between the carbon and the PTFE layer. So it's worked great in terms of stability. But one of the challenge with the PTFE substrate is that now the surface of the PTFE is pretty low compared to the carbon substrate. So what you can see here from this graph, now even though the carbon is not stable, but when we run at the same potential, now we observe much higher current for the carbon, right? Start at 250 milliamp. While at the same potential, the carbon is about, the PTFE is around 100 milliamp current density. So we have a pretty low current density for PTFE substrate. So now the question is there any way that we can improve the current density on PTFE substrate? And that leads us to the second thing here. Now, what is the role of the gas diffusion layer? So with the gas diffusion layer, we bring the CO2 from the gas phase to the interface between gas and liquid, right? That is where the catalyst is located. So if you look on the figure on the left-hand side here, so the PTFE layer, the white layer here, so the CO2 can penetrate through that, no problem. But then when you see that orange layer here, that is the catalyst layer. And in CO2 conversion, the catalyst layer is often hydrophilic and it filled with the water there, right? So you can bring the CO2 to the interface, but you cannot bring the CO2 to everywhere. Now, inside the catalyst layer, it just stays there, especially when you use the basic, you use the alkali catalyte, right? So the basic solution and the CO2 is the acid gas, and then it just combine together, and then it converts CO2 into the carbonate. So you cannot convert the CO2. Right? As you show in the figure on the right-hand side here, the CO2 in the gas phase, and then it can be converted on the copper near the PTFE, but it cannot be transported to the area far from that interface because now the CO2 will be converted to the carbonate before it can be converted. So with this structure, it's only a small portion of the catalyst can be used, and the majority of the catalyst cannot be accessible for CO2. And then we found out it's actually accidentally that when we coat a thin layer of any ionomer on top of the copper catalyst, right? So we still have the copper catalyst, and then we coat them with the ionomer, and then we found that, so you see here like the thin layer of the ionomer on the surface of the copper particle, right? So when we have that ionomer, we can increase the current significantly. Now on this graph, we are showing this is the current density of CO2 conversion current density. It's basically its proportion to how much CO2 you have, right? So without the without the Nafion layer, now the current is only 50 milliamp or something. And then when you have the ionomer on top here, now the current can extend it to 500 500 milliamp current density here. So it's almost like 10 times increase. And based on that, we're trying to understand what is going on in here. Even though we are not 100% sure of the mechanism, but based on all of the control we have, we think the most possible way is that because of the structure of the ionomer layer, where you have the hydrophobic part and then you have the hydrophilic part. So when you coat them on the surface of the catalyst, now it can create a channel for the CO2 to go through, and also like the iron and the water can also penetrate through that layer, but in the two different ways, right? So CO2 coming along the copper and the water is going directly here. So now it's similar to the decouple between the CO2 and electron, but in this case, in the catalyst layer, we create a pathway for CO2 and another pathway for the water, so they don't mix with each other, so that the CO2 can go to on the surface of the copper, and that's why we have high current density. So now by understand, based on that hypothesis, and then we design kind of a 3D structure, try to increase the number of the active site further. So we use the copper nanoparticle, mix them with the PTFE, coat them on the copper on PTFE here. So mix the particle with the ionomer. So on the substrate here, just trying to increase the number of the active site. And by doing so, we now can increase the partial current, which is the current that go to the product of up to 1 to 1.2 ampere, which is now we have the CO2 conversion, which is in like on par with what a hydrogen production technology can achieve, right? Like similar to the PEM system. Of course, the PEM can go much higher, but we are in the range of 1 ampere current density. Okay, so it's worked great like so far in current density in terms of the stability. So what's the problem? Well, the problem coming from the electrolyte that we use. Right, so I show you like two examples, and both of them we use the alkali cathodite for CO2 conversion. And with alkali, we suppress the hydrogen evolution. We can reduce the cell voltage, but we pay a lot of penalty for the carbonate formation. Right, so the CO2 not only converted to ethylene, but it's also converted to carbonate and bicarbonate, so that you need to regenerate your electrolytes, and that costs a lot of energy. So we did some calculation to see like, if you have the CO2 crossover, if you have the CO2 convert to carbonate, now how much energy you need, or like what would be kind of acceptable ratio. And the results of that, like if you have the cost for ethylene of $1,000 per ton, then like you should have very small amount of the CO2 converted to the carbonate or crossover. Right? Otherwise, the energy consumption is way too much. Right? So now, based on this, like what we're gonna do in order to reduce the carbonate formation, the best way to run the reaction in the neutral condition or even the acidic condition, so that you can prevent the carbonates crossover or on a formation there. So we started working on that just by checking the copper on PTFE. We use the same catalyst there, but we do not coat them with the carbon. So even without the carbon layer, the copper on PTFE can also work at the electrodes there, right? And then we use the substrate here, and then we run the reaction. But now we run the reaction in a neutral condition, trying to avoid the carbonate formation. We still observe the descent ethylene selectivity of like around 55%. But the problem now is that we can only run the reaction for only 4 to 5 hours. So as you can see here in these figures, like after 4 or 5 hours, the ethylene goes down, hydrogen go up, and methane go up. So meaning that there's something is going on here. And the problem is not about the hydrophobicity or like flooding, because we still use the PTFE here, and we did not see the water on the backside, and we did not see the zone formation like in this short time and in this condition. So there must be something happen to the catalyst. Okay, so that leads us to the second part of my talk today. What would be the strategy to overcome the stability of the system when there's something happen with the catalyst? Okay, so let's just like maybe review a little bit on what would be the problem that causes the instability of the catalyst, like copper or the other catalyst in CO2 conversion. And in general, you can see like 3 different mechanisms that can cause a problem. Now, the first one is that you have the catalyst, and then you have something in your system, right? So you have some metal ion in your like catholyte or electrolyte there that can be deposited on the surface of the catalyst, like iron, like nickel or iron. So though metal is very good for hydrogen evolution, right? So when it deposits on the surface of your catalyst, not only it blocks your active site, but also now it creates the site for hydrogen evolution, which is the competing reaction. We don't want that. Now, the second one is depend on the nature of your catalyst. Either if it's the oxidizer, right, you have some different oxidation state, right, in your catalyst. So during the reaction, it can change, the oxidation state of the catalyst can change because it's under reducing condition. So like some of the oxide, like if you run copper oxide, gonna reduce to the metallic copper, like zinc or other catalysts. Right? So it's changing the oxidation state here, another thing. Now the last one is quite common for copper catalyst is the surface of the catalyst itself is reconstructed. So it changed the morphology, it changed the surface of the catalyst that leads to the change in the product selectivity. Right? We know that the nature of the active site depending on the configuration of the atom on the surface. And if that configuration change, the selectivity will change. Now, if you look at these three mechanisms and trying to figure out, is there any way that if you have one solution and then you can overcome all three of these problems, then you may think about, okay, one simple way would be trying to oxidize the surface. Now, why is that? So if you have the metallic deposit on the surface right there, right? If you can oxidize it back to the metal, can go back to the solution. If you have the oxide catalyst, now you run the reaction, it reduces to metallic surface. Now, if you oxidize them, you can resume the oxide phase, right? And also, like with the surface reconstruction, you can turn into the oxide and then you reduce them. This also like can change the surface and it can change the activity as well that we discuss later on. So like three different challenges, but potentially we just need one solution for that. Okay, so we don't know exactly what happened with our copper catalyst that I showed previously, but we will try the different solutions based on this hypothesis. So how are we going to regenerate the surface here? So the approach that we use is that we run the reaction for a while and then we oxidize the surface, and then we run the reaction and then we oxidize the surface, right? So it's kind of like you change alternating the current between the, let's say if this is the current, then you apply the current for CO2 reduction. Now, after some time here, you oxidize the surface, right? So you control the current, or you can control the potential to oxidize the surface, like for some time here, and then you reduce the surface again, turn them back into the metallic, right? So you can just repeat that one. And what you can do here is that you can oxidize the surface either by electrochemical oxidation, which is make a lot of sense, right? You have an electrochemical cell can just apply positive current, or like you change the voltage and then you can oxidize your catalyst surface. But you can also use a chemical oxidation. So you can introduce some of the oxidizing agent to your system so that you can oxidize the surface of the catalyst. Right? So we apply the different strategy and we apply for the different metals. But I just want to show like two examples here like for copper catalyst. Okay, so the first one is that we just use the simple like oxidation, like apply the positive current, right? So we run the reaction and then after a certain time, let's say after 5 minutes, we oxidize, or maybe after 15 minutes, we oxidize, or after 30 minutes, we're gonna oxidize. And then we see like how we can extend the reaction time. So in this graph, we track the Faraday efficiency of ethylene. Right? And then, okay, so then without doing anything, we know that it's stable for only 4 or 5 hours in the previous slides. But now if you do the oxidation every 1 minute, you can extend the lifetime to about 20 hours, which is a little bit better, already 4 times. Right? Now, if you oxidize every 15 minutes, well, the steam is still in the same oxidation condition, right? At least the oxidation condition here. But the point here is that Now, by controlling the oxidation and reduction time, you can extend the lifetime of your catalyst. Right? So that it seems like the approach work, right? So you extend the lifetime to more over 100 hours. But you also recognize here there's something, right? So when you extend the reduction time, that means like less oxidation is even better. It's not like the frequency of the oxidation is important here. So we try to understand why is that, and so we analyze the surface of the catalyst after the reaction, before and after the reaction. So on the left-hand side is the morphology of the catalyst before the reaction. And then we analyze it after like 100 or 120 hours. And we observe that a significant amount of the copper leaves the surface, right? So when you oxidize the surface, so you change the local structure, like at atomic scale of the copper, but you also change it in the macro scale. Some of the copper will move from this space to the other space, and then some of the copper will be peeled off from the substrate. And that is the main reason that's called the degradation over time. Even though we can achieve 100 hours, but the copper is still degrade over time. And that's because of the electrochemical oxidation. Now, if that is the case, then you may think if we can control the oxidation in a better way, we may be able to run the reaction longer, right? So we can stabilize the copper surface. And that comes the strategy with the chemical oxidation instead of electrochemical oxidation. So what we did in this work is my postdoc visiting scientist. So what we did in this work is that we use the oxygen to oxidize the surface, right? We do not apply the positive current to reduce the surface, but instead we turn off the system and we introduce the oxygen to the cathode. So that oxygen is going to oxidize the surface of the copper, turn them into the copper oxide. And then we run the reaction again after 15 minutes, right? So you run the reaction for 15 minutes, you turn it off 15 minutes, and then you run it again. Just keep that cycle. And we try to understand what would be the role of oxygen in there. So if you look at this graph, when we do not have any oxygen in the system, so we bubble the CO2 in the cathode, in the anode, so that we remove all of the oxygen. Now the system can stable for only like about 20 hours, right? Now, if you only remove the oxygen in the cathode, so you still have some oxygen in the anode, can migrate to the cathode, so you still have a little bit of oxygen in the system. You can run the reaction for about 50 hours. And if you control the amount of the oxygen inside the cathode, so that you have enough oxygen to oxidize the surface, you can run the reaction for 200 hours. So this is only on time, right? We did not count the off time there. So that means we run the reaction for 400 hours in total, and 200 hours is on time. And we check the surface after the reaction, and it looked kind of, well, we see like the micro scale is changed, but in general, you still have some copper, the same morphology of the copper. And we also use exactly the same strategy, but we want to run the reaction at much higher current. So this is a 1 ampere current density, and the previous one is 150. And in order to run a high current, so we need to make 3D catalyst. We need a lot of active site. So we spray the copper nanoparticle on the PTFE, and then we run the reaction at 1 ampere. And then we can extend the lifetime from about like 5 hours up to 30 to 35 hours, having the pretty good selectivity, like 40 to 50% of ethylene. So the hypothesis work, and with the running the on-off, it can help with improving the stability of the system. But we could not run it longer. Right? We want to run for a few hundred hours. We want to run 1,000 hours, but we can't. We need to stop at 35 hours. And the reason for that is because of the zone formation. I haven't discussed it before, but zone formation, when you run the reaction in neutral media, is one of the big problems. So even though you run the reaction, you have the liquid there, but the zone is accumulated on the surface of the catalyst, penetrate through the gas diffusion layer, inside the gas diffusion layer, and then you go to the backside here. So as you see here in this photo, like after 35 hours of the reaction, you see a huge amount of zone here, which is potassium bicarbonate in this case. Like it's completely blocked the gas diffusion electrode. And when it is blocked, like you do not have enough CO2, and then the system goes down. And that is other than the flooding problem, the zone problem is another problem in CO2 conversion, which is not easy to solve. And this is still, until now, is one of the challenges in CO2 conversion. So now you may need to think, I'll just give you a minute to think about, like what I discussed so far. I use gas diffusion layer for CO2 conversion at high current density. And then we have three different problems. So we have the flooding problem, which we solve by the PTFE gas diffusion layer. We have the catalyst problem, but we can do that with the on-off, the oxidation, in situ regeneration. And we have another zone problem. We don't know how to solve it. So there are three different problems, but two problems linked to the gas diffusion layer, and one problem linked to the catalyst layer. So you may ask, like, can we do CO2 conversion at high reaction rate, but without the gas diffusion layer? Can we stop using the gas diffusion layer in CO2 conversion? And that is the last topic of my talk today. I'm going to talk about how we can achieve high rate CO2 conversion, which is at high current density, but using the CO2 in the aqueous phase. It's not the gas phase. We do not use the gas diffusion layer. So when I look about this one, I look at the different system for CO2 conversion in the aqueous phase, and I'm really interested in the cell configuration. It's called the bicarbonate electrolyzer. And this cell configuration is invented by Professor Curtis Buttigieg at the University of British Columbia here in Canada as well. And what happened in this system is that instead of feeding the gas CO2 into the system, now you use the bicarbonate in solution, right, with a very high solubility there. And then in this system, when you fed it here, now the bicarbonate can be converted to the CO2. So the CO2 now is generated inside your system, inside your electrode, right? So that CO2 is different from when you feed the CO2 directly in the solution, right? So this is the configuration of the cell. Often you use the bipolar membrane. You can use the cation exchange membrane as well. The working principles are the same. The proton going from the membrane or from the anode go to the cathode side. The proton react with the bicarbonate, generating the CO2 inside your system. Depending how you construct the system, it can be inside in your electrode, right? Now, if you want to improve the current a little bit further, you can also combine with the dissolved CO2, similar to the other aqueous system. So I can have two sorts of CO2. I can have dissolved CO2 in the solution. I can also have the CO2 that generated from bicarbonate. So two sorts of the CO2. Can we have the high current with this structure? Now, to answer that question, we first do some simulation. Now, assuming that we have the electrode with a different porosity. And we assume that we had the best ever catalyst. So we either the catalyst with a pretty good like activity, right? And then we do the modeling here either for the methane production and methane Faraday efficiency versus the current density in the different scenarios. Now, two main scenarios is that we use the porous structure, which is dense, which is a small pore and less porous. So we call the dense structure over here, right? And the other one we call the open matrix, which is like 3D a large pore electrode, so with a pretty good diffusion, right? So if you have like two scenario, and also we also consider this one is nitrogen bubbling or CO2 bubbling. So when you have the CO2 bubbling, that means you have both CO2 source. You have the CO2 dissolved, and then you have the CO2 from bicarbonate. And without that CO2 bubbling with the nitrogen here, you have only one sort of CO2 from bicarbonate, right? So now we have the different scenario here. And the interesting thing here is that if you can find something with the right porous structure, with the right activity, you can achieve like methane selectivity of 60 to 70% at the current density over 400, 500 milliamp, which is great, right? So we are targeting the current of 200 milliamp and above, but now we can even achieve even much larger current. So it's all work out like perfectly. Now the main task for us is to choose what would be the electrode. So we set out to see what would be the best electrode, and then the best way to get that is looking at Amazon to see what kind of copper electrode that you can find. And we found this one. So we found the copper mesh, like with 150 to 200 mesh, which is like the pore size of about 100 micron. You see it from the SEM here. So it's open pore, right? The pore is about 150 micron, and you have the mesh height of the Y of about 100 micron, right? So this mesh is that people use this in the garden, use this in the window just to prevent the insect. But it seems that it has the right structure. So how does this perform in our system? So our student here, like Cornelius and Fei, well, by the way, Fei is Chinese student who has the CSC scholarship, who is doing one of my first PhD student. So now they put together, and then they assemble the cell. Look on the left-hand side here is similar to the membrane electrode assembly cell, if you are familiar with that. Right? So it's very stick together, cathode, anode, and bipolar membrane in between. The only problem is that when you run the reaction at a fixed current density of 250 milliamp, it's only hydrogen is produced. It's produced more than 90% of hydrogen. We did not even see any like methane, less than 1%, and no other product. And this is a little bit disappointing, but also it's kind of expected, right? So you are using a copper coming from Amazon and then using the people use that for in the garden. So what do you expect? So we want to find a way, how do we activate them? How do we make it work? So we think of a solution. So like Professor Matt Cannon at Stanford, like already discarded like 10 years ago, that with the copper surface, if you oxidize them a little bit, you can improve the selectivity of CO2 conversion, right? So we did exactly the similar thing. Like we tried to oxidize the surface. So let me explain this graph and how we did, right? So now in the first 40 minutes, we do the oxidation of the surface, right? So we apply constant CV there between the negative and positive current so that we oxidize the surface of the copper. Now, after 10 of that cycle, we stop that, and then we start the reaction. So we start the CO2 reduction after the CV, and now we start seeing the methane formation. right? Now from zero methane, now you have more than 20% of selectivity for methane. Hydrogen go down to about 50%, which is a very positive. But the problem is now when you keep running the reaction, the selectivity go down quickly here. And that's the challenge. And we don't know the reason, right? So what we thought is that probably maybe we create something active, but because it's so unstable, that the selectivity go down quickly. And if that is the case, what can we do? So our two students, like they came up with the idea of how about we keep making oxide constantly in a very short time. And the way that they did is that they run the reaction for only about like 10 to 20 seconds. And after that, they oxidize the surface is like within like 1 to 3 milliamp positive current to oxidize the surface. Right? As you can see here, the oxidation current is way smaller than the reduction current. Right? So it's only enough to oxidize the surface layer of the copper. And we also use a very short time for the oxidation. It's not a very long, right? It's a very small current go to the oxidation compared to the current go to the CO2 conversion. And now when we measure the selectivity, now the methane selectivity can stable for about 3 hours, staying there at about 60% of selectivity, which is amazing. Now the question is, what is going on in here and why do we have a surface that can create the methane, right? So we try to understand by observing the surface with the ESEM. So as you can see here, when you start before the reaction, it's pretty smooth. And then when you run the reaction as a constant current, it creates some particle on the surface here. We don't know exact the mechanism, but probably the copper reconstruction. But what we quite sure here is that in the surface of the copper, when we do the alternating current between the positive and negative, it creates some kind of a porous structure. So we think that like this feature of the copper is the key for the methane formation, even though at the atomic level, we are not kind of like exactly what is going on at the atomic level because we could not characterize them like in situ here. But we think that like the methane is related to the surface of the copper. And if that is the case, then we can tune the condition so that we can change the surface of the copper, right? And that's exactly what we did, like by applying different oxidation reduction condition. So less oxidation, that means you have very long reduction, and then you fix the oxidation of 5 seconds. Now medium is like 15 seconds of reduction and then 5 seconds of oxidation. And this one is, the last one is more oxidation, right? Half of the time. Much different in current though, right? So now you see that you have the different surface. And also like with the different surface here, you have the different selectivity for methane, right? With the less oxidation, you have 65, 67%. Like all of them are as the current density of 250 milliamp, right? And also like increase the oxidation, you increase methane selectivity to 70 to close to 80% here. So there's strong link between the oxidation condition, the surface morphology, and the methane selectivity. Now, one of the questions now you may ask here is that, now this is a good thing. Okay, so if you activate the surface, you create this structure. Can it be stable? Like, or do you need to keep doing the oxidation? Or like if you create a right structure and then you can keep running reduction only, right? We don't know what happens. So we're trying to design an experiment to understand that. And the interesting thing here is that when you start the reaction and then you have a very high methane selectivity, right, alternating current, But as soon as you shrink it to the constant current, like only reduction without oxidation, now the methane drops very quickly here. Okay? So that means the constant oxidation is a requirement to keep the selectivity. Now, another interesting point is that, okay, now the methane goes down, and if I apply the alternating current again, then the methane go up, right? So that means somehow the surface is a little bit reversible in this case. Like even that when the surface is deactivated, you can reactivate it again. And that's the main message here. Okay, so I have shown you like, oh, it's a pretty good selectivity and the reversible property. Now, the question is, how does this compare to the gas phase conversion? Right, so in this graph, we compare the selectivity versus the CO methane partial current density of the aqueous system in our now, even with the aqueous system, we can have selectivity and high current density as well compared to the gas phase CO2. And it's not just the selectivity and the current density, right? We also want to compare the energy efficiency, which is the overall cell voltage. How much energy do you need for making the methane? Now, on the left-hand side, you see when we compare with the MEA and the other system, we still have the better energy efficiency compared to the previous MEA or bicarbonate system, right? And another interesting point, which I like about the bicarbonate conversion system, is about the product concentration. Now, because we feed in the liquid, right, and then you make the methane, which is the gas. So the methane is automatically separate from the liquid, so you have the pretty good separation. And then you have the pretty good methane concentration in your system. And that reflects in this graph on the right-hand side. In our system, we have methane concentration from 15 to 20 something percent, while most of the previous work on the gas phase has like less than 10% of methane. And why this one is important? Because the separation cost of the methane will depend on the concentration of the methane in the stream, right? So that's another good thing. Now, one missing point here. All right, what about the stability here? So in the previous slide, I showed that for CO2 to ethylene, we can run for 100 hours. But in this system, we can only run for less than 20 hours. And in this work, we show here that we can run for 12 hours at 250 milliamp, and also like 12 hours, a little bit more than that at 500 milliamp current density. The methane is stable at 70% in both cases. So what is going on here? Like our group is focused on the stability, right? So we are not satisfied with the reaction like running less than 100 hours. We try to understand what is going on here. So when we look at the substrate, like after very long reaction, like after 20 hours, by that time, the ethylene started decrease. Sorry, the methane started to decrease to about 50, 60%. And at the same time, ethylene increased. And if you look at the surface of the substrate, you see a clear difference, right? On the left-hand side is the surface to make the methane. On the right-hand side, it started making ethylene. Wow. So methane go down, ethylene go up. It's increased the porosity of the substrate. So that means when you constantly apply, you're changing the current, the surface of the copper keep changing, and it's increase in terms of the porosity here. And the higher porosity of the substrate more likely we increase the formation of the ethylene. And that is one of the challenge that our group is now focusing on, is that how do we control the growth of the copper? I cannot tell you exactly how we are doing that, but we are confident that we can control the growth of the copper so that we can keep high methane selectivity. And that is the ongoing work from Fei, who found a way to stabilize the growth of the copper. And now we can keep the reaction running for 600 hours, keeping the selectivity around 70%. Right? So we go from 10 to 12 hours now up to 600 hours, and hopefully that we can extend it further based on the strategy we are developing right now. All right, the last slide that, okay, this is the final thoughts, is basically I have one slide for probably the student or someone who has just started working on CO2 conversion, or someone who wants to work on this area. Now, in CO2 conversion, now we know that the catalyst is very important. The catalyst is like a heart of the system, and it controls the selectivity, it controls the efficiency, but also there's other part is also important as well, right? If we want to develop CO2 conversion technology, you will need breakthrough, not just in the catalyst, but in all of the other area, membrane, cell configuration, all type of optimization, because this is very different from the hydrogen production. You don't have to care about the selectivity. Now in CO2 conversion, you create a bunch of different products. So focus on what would be the optimum cell configuration is still like unknown question. Right? So there's another thing that you can focus on, and there's another room for the breakthrough in CO2 conversion. Now, the second one is what we are trying to do, which is I love about, like we always think, okay, so an electrolyzer is like a human body, right? So the way it works is that, you can have a small child, which is healthy, perfect child, but there's no guarantee that you have a healthy adult, right? So it depends on how you operate it and how you live. And it's like the electrolyzer, like how do you operate the electrolyzer is very important for the stability of the system. And this linked to one of the points is that I think that the talk in the, 2 days ago, a professor talked about the dynamic of the surface of the catalyst, right? So the catalyst is always dynamic during direction. So why should we keep running at the steady state? Why don't we just adding another level by changing the dynamic of the catalyst here, running at the different potential, different current at the same time, right? So just trying to further improve the efficiency of the system. So I think that is the two messages that I want to tell the new young student who want to work on CO2 conversion. And with that, I would like to thank my group here, like the main member of the group. We have Faye here, Cornelius, and Toon is the work that I show here, and of course the funding agencies. And thank you again, and I'm happy to answer your question.
Hi, Dr. Dinh. Thanks very much for your wonderful talk. Very interesting work. You show us the strategies you developed, very important to improve the CO2 conversion, the selectivity, or of course also activity. Yeah. And you also mentioned the three strategies, how to control mass transport of CO2 gas. As part two, for example, in situ regeneration of catalyst for long-term operation, and how to achieve high-rate CO2 conversion from aqueous solution, improve the stability. Very important. Thank you. Also, I learned a lot from your talk. Thank you.
Oh, thank you. Yeah,
so I just
yeah,
for the audience in different live platforms, if you have any questions, you can directly communicate with Dr. Dinh, or also you can type words. Our staff will collect the questions from different live platforms. I will ask a question on behalf the audience. Thank you. So, Dr. Dinh, very interesting work. I have one question.
Sure,
So,
go ahead. Yeah.
for part two you mentioned just now, for
Mhm.
on off the oxidation reduction
Yeah.
process, yeah, just alternating the current density or maybe
Mhm.
potential. Yeah, you mentioned that. Yeah, just improve the generation of catalyst, improve the stability. Oh, yeah,
Mhm.
yes. This strategy is very important and very useful. Yes. So I have one question. So I think can you just control the potential or current density for example copper is not fully oxidized or copper ions not fully reduced. So if we can control the density or potential voltage, if the mixed valence state for copper, for example, 41 or 0, yeah, mixed valence state, maybe I'm not sure. Maybe it's better to facilitate the C2 production products.
Mhm.
For
Yeah.
example, ethylene or ethanol like this. Yes, because it is already reported the mixed valence state for copper
Mhm.
is better to improve the C2 production CC coupling. Yeah. So what about your idea for this one?
Mhm.
Thank you.
No, I think that is a wonderful idea, and we have thought about that. We don't know how to do that, but I think it's doable. Like what you already pointed out, of course. Now just rephrase that, like what you said, the importance of the oxidation state of the copper, right? If we can control, is this a copper one? It may be making more C2, right? And the question is how can we control the oxidation, the condition to create the copper one? And that's a great question. And I think in principle, we should be able to do that. But now it maybe is a little bit complicated because when you do the CO2 conversion, you have the copper surface only exposed to the alkali condition. Well, maybe you have the hydroxide on the surface, right?
Yeah.
So often, maybe in that condition, the copper tend to oxidize directly from the copper metal to copper 2 ion. So maybe in order to kind of slowly oxidize or something that to make the oxide phase like copper 1 oxide, for example, then you may need something on the surface there, which is more stable. Or like what I'm saying is that you can add it or you can control the local environment on the surface so that when you oxidize, it's prefer copper 1. For example, maybe you can have the iron in there, like chloride iron. So halogen ion, like chlorine or bromide or like chloride, right? So when in the presence of the chloride there, when you oxidize them, it's gonna produce the copper chloride. And the copper one chloride tend to decompose and then it can make the copper one oxide. And that is actually demonstrated like people have used that strategy to modify the surface of the catalyst, right? So you can do the oxidation, but you control the environment so that it goes through the different stage and it end up making the copper one oxide nanocube or something like that. And it's improved the C2. We haven't done that in our work, but obviously that is one of the interesting area that make running the oxidation reduction even more interesting. But that is a great idea. And I think they still like not just our group, but the others started looking at that as well.
Oh, thanks for your detailed response. Yeah, thank you. So for the audience, I also checked the Bilibili live platform. More than 1,400 people are listening to your talk. So many.
Right?
The
Yeah.
early this live platform. If you have any questions, welcome to directly communicate with Dr. Ding. For those Tencent or we, yeah. Also, you can directly communicate with Dr. Ding. Thank you. So also, I'll start. Yeah, transfer the question to me. So I will ask a question on behalf of the audience.
Sure.
One question. Let me see. I just translate the Chinese. Mm, for the sponsors, yeah, in the industrial. Uh, so what are issues they care about. For example, which issue, which problem, or especially the indicator. Uh, so do you?
Okay, that's a great question. Like for industrial, well, everyone it depends on the products, right? But in general, you have the few different performance metric in CO2 conversion. Um, well, you have the product selectivity, you have stability, you have the reaction rate, you have the energy efficiency. But for industry, well, often they look at the overall picture, right? So because all of those performance metrics are linked to each other. Like you have the selectivity, you have current density. When you run at higher current density, you will have the lower energy efficiency, right? And then like, it's same for selectivity. So a combined performance metric, like taking into account all of those components, would be there's interest. And if you break down what would be the key thing in there, let's say if you break down the cost of, let's say, ethylene production from carbon dioxide, and you see the dominant cost is the electricity cost, right? So if that is the electricity cost, then you want to have a system with the higher energy efficiency. And in that case, you will need to run the ration with the lower cell voltage. And often, like cell voltage is one of the critical components that most of the industry care about, right? So, and then also, like if there is other product, will have the different thing. So different product will have the different criteria, and then you may look at in the different way. But I would say like the energy efficiency is a critical important for if we want to lower the price based on electricity, the current density, you want to have it at a certain current density to reduce the capital cost, right? And it's also depend on the cell configuration, the capital cost will be different. So it's a very long answer to your question, but overall, like you will need to look at the connection between the performance metric and then to see what will be the key thing that control your cost.
Okay, thank you. Thank you for your reply. Another question from the audience. Ask 3 times. How to, just like you mentioned, I think he wants to know about bipolar membrane. Yeah. So how to get bipolar membrane?
Oh, okay. Well, the bipolar membrane is well, that's a great question. We have some problem with bipolar membrane as well. Like every time we buy the bipolar membrane, we may have a different one. The performance is different, which is quite challenging. But so far, we only buy the bipolar membrane from fuel cell store, and that's the only place that I know. We try to buy some bipolar membrane also directly from China. I think that in Alibaba or like somewhere. But that bipolar membrane is used for maybe more about the water system, and it's pretty thick and it doesn't really work for CO2. But if you go to the fuel cell store, that bipolar membrane, that's what we are using right now.
Okay, thank you. So, any other questions?
Hello.
Okay, Professor Liu.
Questions.
Okay.
Sure. Yeah.
Okay. Hello, Dr. Ding. Yes, glad to see you online. So, you give us a very nice talk, and I also learned so much in your talks. So I'm very interested in your work of you use a very special strategy to extend the stability. So, in my opinion, when you use copper as a cathode catalyst, so when we apply the potential, the copper, I'm not sure. I don't know what's the initial state of the copper you used in your catalyst. And when you apply the potential, the copper, I think the valence state of the copper will change. And if you use if the initial copper state is 0, and when you apply the potential, what does it change to 0 or to high valence? And when you oxidize it, and what is that change? And another question is when you use oxidation and reduction to extend the catalytic age, and I note that the surface change obviously, and I think both the chemical property and the physical property changes. So which one is important to increase your activity during the between these two changes? So
okay, that's a great question. Wow, that's like two great questions actually. So I'm gonna go through the first one. Like in short, we use the metallic copper to start with. So we use the physical deposition of the copper, which is, of course, like it's the metallic copper, but also like you expose to the air, maybe on the surface of the copper would be like there's some maybe oxide there. But what we believe is that when you run the reaction, we often they do the CV like to reduce the surface before we run the reaction.
Yes.
So we believe that like before the reaction, mostly the surface of the copper is metallic.
Oh.
And now the question is when you oxidize that, what kind of copper we produce? We perform only the in situ Raman to see what would be the oxidation state of the copper. We see there's some kind of like oxide, mixture copper 1, copper 2 oxide on the surface, some carbonate copper. We are not quite sure on what exactly the dominant component in there because we do not have the in situ XAS. But it seems that we have the mixture of the oxidation state. But I could not like give you like kind of more detail exactly like
I think what
would be the composition there, right? Now the second one is that okay, so you change in terms of the oxidation state, you change in terms of the physical morphology of the copper. Yeah. Which one is more important? I don't know. So this is like linked to the one of the great question that the whole community is trying to answer, right? So like, what is why the oxide copper work so well? Yeah. Is that because of the oxidation state? Is that because of the some oxygen remaining subsurface? Or maybe it's just because that when you reduce the oxide surface into metallic and then you create the chain in terms of morphology, right? Yes. So, well, what we observed so far, we are quite confident that the morphology chain is important. Of course, it's play a part. What we don't know is that we do not have any direct evidence in our group in the link with the oxidation state because we cannot have the in situ characterization like while running the CO2 conversion, right? So we need to measure the performance and characterize the copper at the same time if we want to link between the performance and the oxidation, and we could not do that. But I am quite sure that the morphology played an important role in the selectivity in our system. And there is two components in the morphology. Like you mentioned, like in the micro scale, which is when you do the oxidation, is at the atomic scale, right? So you oxidize the surface, you reduce. So at the atomic scale, the copper chain, and that is important for selectivity. Now, the other one, which is macro scale, when you oxidize the copper, like you turn the copper into the oxide and hydroxide, but some of the copper will be leached to the solution because even though you have the copper hydroxide, it's also dissolved a little bit in the solution, and that copper migrate to the other place, right? So from the macro scale, some of the copper will be leached and then it deposit on the other position. So the whole morphology chain, and that chain, it causes the damage for the stability of the system. And the micro chain is good because it improves the selectivity.
Okay, thank you very much. Thank you.
Thank you, Dr. for your detailed response. So any other questions? Okay, If no other question, if you have a question later, or you can directly send an email to Dr. Dinh. Yeah. Thanks again.
One last comment. I'm looking for a new postdoc and graduate student. If you are interested in working with me in my group, feel free to send me your CV.
Right. This year? Very good.
Now we are recruiting now. Yeah. Starting. So
how many?
international student will start from this September, and the postdoc will be started as soon as possible. We are looking for a couple of postdoc and a couple of PhD students.
Okay, very good opportunity. Thank you. Thanks again for your wonderful talk and detailed response to all questions. Thank you. Also, welcome to visit the channel, Tianjin University. Give an offline talk in future.
Sure, and, I would love to. Thank you so much.
And also welcome to submit your work to Smart Man anytime. It's fine.
Sure.
Thanks again.
Okay.
So late. I think it's so late for your time. 9:50 p.m.
Yeah, it's 9:50 now.
So I have to say good night.
Thank you. Okay. So have a wonderful day.
Okay. Thank you.
Okay.
Bye.
Bye.
Bye.